Hello, I'm very pleased to be here, and I learned a lot in these 2 days. And I'm not sure I can match the contributions of the other people who have devoted decades to generating cohorts and following them for a long time. But I will try to do what I can, and I hope at least some of it is useful and impactful. So as Dee mentioned, I'm the Chief Scientific Officer of the Autism Impact Fund, and both in terms of disclosure and to give you some idea of what the AIF does, make a short introduction. The Autism Impact Fund is a venture capital fund, and the venture part of me was quite excited to see the virtual reality company XR Therapeutics. So the idea behind this venture fund was that there is a substantial amount of federal funding and, well, not enough, but reasonable amounts of federal funding. And there is academic research, there is philanthropy, and there is advocacy. But there was no venture fund that would bring ideas to market and make them self-sustaining and make them democratizable. So this was the institution of the fund, which is about a couple of years old now, was to add a missing piece that would complement all the other activity going on in autism. And the prime movers behind the fund all have high needs autistic children. So that's where the impact part comes from. So this is a mission-driven venture capital fund. So my talk for today is going to be in response to the framework for response to aging and autism that Autism Speaks outlined. And I'm going to be on this axis, mostly talking about the biomedical and clinical research with a little bit of knowledge translation. And as we heard from so many people, agency and choice are vital. So, but having said that, biology is a foundation to a lot of what is going on in autism and also in aging and autism. If we ignore biology, then we squander gains made from other intervention. For example, successfully mainstreaming a child into a regular school, but not addressing the sleep needs of the child, and if the child sleeps poorly, then you're squandering gains made in school, because learning and sleep are very closely associated. So essentially, the idea is not to medicalize everything or not to make biology the absolute foundation, but to make sure biology is accounted for everywhere we can, and to make biology a complement to all the social and systems interventions that we have been talking about for a couple of days. Wait, why won't the slide turn? Okay, let's see. Okay. The next couple of slides refer to this very famous study by Lisa Krohn. And the point doesn't need to be labored here. Everybody knows this. And we are looking at the fact that there are a whole number of comorbidities associated with autism and autistic adults. The odds ratio is up for just about everything you can imagine, significantly up for many, say Parkinson's disease, for example, the odds ratio is 32. So very significant compared to neurotypical. And again, this extends to gastrointestinal disorders, sleep, nutrition, other conditions, and renal disorders, and so on. So that is the baseline. There are extraordinary number of comorbidities associated with ASD, and if you don't really understand where these come from and what is it about ASD that drives increases in these comorbidities, then we will not be able to help people live the full lives that they deserve to have. And again, this is just the same points. Even rare conditions, just stroke and Parkinson's disease, are significantly more common, and much research is needed. And the question is trying to figure out exactly what kind of research would be most impactful. So the brief for me was to think about therapeutics, but when I'm speaking about therapeutics, I mean that therapeutics not just for autism, which is not the fact I'm considering, but in dealing with treating all these comorbidities that the person experiences in the course of their lifetime, and multiple comorbidities and the heterogeneity that tracks along with all of this. And this is just a cartoon to show that this would include any kind of multi-omic molecular approaches, genomics, transcriptomics, proteomics, metabolomics, none of which exist on the scale that they ought to exist to really address the needs of the ASD population. And the sorts of questions one might think about, big umbrella questions, are what is the nature and range of response to therapy in autistic individuals? What are the effects of lifelong medication? Can multi-omics be informative? And what is the response to therapy, given that autism is highly heterogeneous, that it's a spectrum, that we know nothing or very little about molecular or physiological subtypes, and that there are no biomarkers. So how do you make advances from a biomedical point of view without biomarkers? So I'm going to use precision oncology as a guide, not because cancer is the most important thing that could happen to you, although if we live long enough, pretty much everybody will get cancer, but because precision medicine is most advanced in cancer. And there are good lessons to be learned. There are cautionary lessons to be learned. And my background most recently is in breast and colorectal cancer with a multi-omics, genomic and genetic perspective. And there are a lot of lessons to be learned there. And my participation in the work at the Autism Impact Fund is to explore to what degree can notions of precision medicine be translated from oncology into autism, neurodevelopmental disorders, and what we think of as associated complex chronic conditions. And at the outset, we should be warned that cancer is in some ways, not that it is solved, but it's easier to think about, because you have access to the material you're studying. You can put your hands on the tumor, either a biopsy or surgically. And the goal is, in principle, straightforward. You're trying to eliminate the tumor. But ASD is more complex. Essentially, what you're trying to do in autism is trying to fine-tune a system that we don't really understand. We don't understand the basics of autism, and we don't understand where these comorbidities come from and how they evolve and how they track. And there's a lot of things we know we don't know. And for this talk, I'm going to present a few vignettes from oncology. One is about cancer incidence, cancer metastasis, cancer immunotherapy and age, cancer immunotherapy and the gut microbiome. And my plea at the end, and the segue that Marcia Malik and others, and Jeremy Parr and others mentioned just in the previous session, that we need to find ways of leveraging EHRs and so on is absolutely critical. So I'm going to end with a plea for robust systems for ethical data sharing, and it'll make more sense as I go along. So a paper just came out on cancer risk in individuals with autism spectrum disorder. This was population-based cohort. This was just released this past week, I think 3 or 4 days ago. This looked at 2.3 million individuals born between 1987 and 2013, followed for 30 years. So this had large cohort population follow-up, independent collection of ASD and cancer, detailed phenotyping, extensive adjustment, sibling comparison design, and genetic correlation analysis for the entire cohort, and the paper is referenced here. The bottom line of the paper is that in ASD without intellectual disability or birth defects, there was no increase in the hazard ratio, in the odds ratio. So they were pretty much, where cancer was concerned, they were more or less similar to the neurotypical. But ASD with both intellectual disability and birth defects were about almost 5-fold higher risk for cancer. Now, if you look at the biology of it, that was just to point out that cancer risk is much higher, and so is the risk of so many other comorbidities, as we saw. Now, if you look at progression, you can see this is just, again, a vignette. A molecule called methylmalonic acid, which is a byproduct of propionate metabolism, is upregulated in the serum of older people and seems to be fairly strongly associated with tumor progression, which is metastasis. And in ASD individuals, 2% are below the reference range, but 13% are above the reference range for methylmalonic acid. And levels as autistic individuals change are not known. So here is one unknown. I'm just using this to point out that there are unknowns even related to cancer, given a population that is 5-fold higher risk than neurotypical for cancer. The next vignette is about immunotherapy and age. So this is a very busy slide, but the only things to consider here are on the left are patients less than 65 years of age, and on the right are patients greater than 65 years of age. Now we're talking about therapy here. We're talking about immunotherapy, which I'm assuming everybody here knows that is the hottest thing in oncology right now. And we don't know who it will work for predictably, but when it works, it has brought people back from the brink of death. And one of the most famous cases being President Jimmy Carter, who had metastatic melanoma and is still doing well 5 or 6 years after diagnosis because he was a wonderful responder to immunotherapy. And one of the reasons that it worked very well for him is that for reasons that are not entirely clear, there are some hypotheses, that people over 65 years seem to respond well to immunotherapy better than younger people. So all of these are better responses compared to this, and we'll discuss that a little more in the next slide. So here, again, the same data, immunotherapy and age. So you're comparing less than 65, greater than 65 in pairs. And you can see that the hazard ratio goes down in almost every case. So for example, for melanoma, less than 65.72 and greater than 65.57. So if you're older, you're likely to do better with immunotherapy for melanoma than if you're younger. What is going on here? Now, this is a cartoon that gives you a rough hypothesis of what is going on here, just to contextualize it. If you're a young female, the strength of the immune system is pretty high. And as you age, the strength of the immune system decreases. The strength of your immune response decreases. And what does this mean in practice? Everybody gets cancer cells all the time, but they are edited out by the immune system. You never see it, you don't feel anything. So that's the immune interaction with these are cancer mutations. And as the immune system sees it, it eliminates those mutations. But paradoxically, what this ends up meaning is that when you're diagnosed or when you present with cancer, as in young females, for example, all the mutations that are driving the tumor that was diagnosed in you have, by definition, escaped immune surveillance. So this is a tumor that learned to avoid the immune system. So it is least visible at the moment to the immune system. But then as you grow older, the one way to think about it is to say your immune system has sort of forgotten how to deal with these things. And you have a mixture of things that have escaped immune surveillance and mutations that exist that are still responsive to survival. So if you use immunotherapy, which essentially is an effort to crank up your immune system to attack your own tumor, then the curve is the opposite of what you saw here, meaning immunotherapy is least effective in young women, but most effective in older males because their immune system, quote unquote, can be retrained because it's forgotten so much to detect tumors. So here is a very direct age-related issue in cancer. And we know that there's a 5-fold higher incidence of cancer in autism, but we don't know whether the immune responses are the same. We have no idea. And the last vignette I'm going to present is about the gut microbiome and autism spectrum disorder. So these are just papers. I'm not going to go into this in detail, but here is a very significant, important paper that says bile acid biosynthetic pathways are enriched in the microbiome of centenarians. So if you have these beneficial bacteria, then you're likely to live longer. And in autism, there are very controversial results. One says there is an altered composition and function of intestinal microbiota in autism. And this is a systematic review that covers a lot of studies. And we know for certain that the microbiome is different, but whether it has any causal connection to autism itself and to general health, or whether it is driven by the finicky dietary preferences of autistic individuals is not understood. This paper here argues that it is the finicky diet that contributes to the microbiome, and it may not have anything to do with autism per se, but it would have something to do with general health, and we need to know what that might be. And one reason is here. Again, this is a very famous landmark paper just published about a year ago, which shows that in melanoma, when you apply anti-PD-1 therapy is a kind of immunotherapy. When you apply immunotherapy and give patients a fecal microbiome transplant from healthy individuals, then people with melanoma here are fall into two classes. All the red ones are non-responders, meaning their tumor grows, but there are a whole bunch of people, these blue lines represent people for whom the fecal microbiome transplant was beneficial. So they did better than they would have done without the beneficial microbiota. So that is very, very significant. And you can see the obvious connection that this has to autistic individuals, not just in the fact that they may have a suboptimal microbiome to deal with their cancers and so on, but if you engraft a microbiome, if you do a microbiome transfer from a healthy individual, will it engraft? We don't know that because these individuals are still eating their finicky diet, and you don't know whether it will engraft. We need to find out what the rates of engraftment are and what you can do to engraft a better microbiome that would contribute both to their gut health and to their general health and to response. Now I'm going to change a little bit from cancer to some immune aspects that have recently become available. Again, just a segue from immunotherapy to general immunology, ideas of neuroimmunology. So the brain was thought to be immune privileged, but now that is considered to be an outdated idea. So there's a substantial crosstalk between neurons and immune cells. And one of the recent findings is that brain meninges are highly immunologically active, and there are channels that can carry some of these cells from the meninges into the brain itself. And the skull, the bone marrow of the skull, is a local source of immune cells. And there is talk from the brain to the bone marrow of the skull and from the skull to the brain with using cytokines that are that have an neuroimmunological effect on the brain. And for a specific study, it's been shown in preclinical models, again, this is not entirely established in humans, that IL-17A modifies autism-like symptoms in preclinical models. And this may have relevance to the relapsing remitting form of ASD, meaning many parents report that children, when they have a fever, which drives IL-17A up, the kids do a little better with their autistic symptoms. So there's a whole world of neuroimmunology that is opening up, and we have no idea how that pertains directly to autism. And there is a company now that we reviewed, but I'm not invested in yet, that is studying some of these and developing interleukin maps of the brain, which I think has the potential to have a very dramatic impact in autism. So one of the arguments that I would like to make is that we simply do not have enough data to seriously tackle biomedical aspects of aging and autism. And somebody asked, where are the gaps? The agenda for this part of the agenda for this meeting is to find out where are the gaps. I think where this question is concerned, it's all gaps. And I would like to make a little detour to make my argument, and based on some very recent findings that implicate Epstein-Barr virus in multiple sclerosis. Multiple sclerosis was first officially rigorously defined in 1868. And now 150 years later, a couple of months ago, we had a paper that conclusively linked Epstein-Barr virus to multiple sclerosis using an autoimmune mechanism, meaning everybody on the planet, pretty much 97%, are exposed to EBV by the time you're 3. So everybody has it, but some small proportion of people go on to develop multiple sclerosis later in life. What is happening here is that your body makes antibodies against EBV, against the EBV EBNA1 protein. And these antibodies in some people go on to attack the myelin sheath and the immune system. And now the target is known as well, which is glial cam. So you generate antibodies against a viral protein, but that viral protein is a molecular mimic of a cellular protein, and the antibodies attack, and you get multiple sclerosis. Now, why am I mentioning this? This causal link, which is very dramatic and very impactful after 150 years, is made possible by this. This slide is very busy. I just want to make one point. This was made possible by access to blood samples from active duty military personnel, 62 million blood samples from 10 million individuals. That is the scale of data that it took and blood samples that it took to address this question conclusively and answer it definitively. And that's the kind of data we need. I'm continuing with this theme of data. Here is a very interesting paper. We talked a little bit yesterday about brain shrinkage, and people were both the autism advocates and some of the speakers addressed brain shrinkage. And today, Blair addressed the shrinkage as well. And this is just a cartoon that shows shrinkage of gray matter volume, ventricular volume, white matter volume, cortical thickness across age. But that is not the point that I'm trying to make. This is the data in the paper. But this took 120,000 brain scans. And the quote here is that to amass so many data sets is akin to a diplomatic masterpiece, says Nico Dosenbach, one of the authors. And this is the scale on which researchers should operate when aggregating brain images. But my point here is that this should not require a diplomatic masterpiece. We should have mechanisms and frameworks in place to be able to access this level of data to answer questions that require that level of data. And increasingly, as we use machine learning and artificial intelligence, these are very, very data-hungry applications. And we need the data, and we do not have systems, especially in autism. These systems are very advanced in cancer. And for people who are interested in it, I would recommend looking up a company called Owkin, O-W-K-I-N. And some of the things they're doing in cancer is quite enlightening. And if you want a more economic commercial viewpoint, Sanofi just invested $120 million for a project with Owkin, and Bristol Myers Squibb invested $80 million for another project that is large-scale, data-driven to design better, more effective, cheaper clinical trials. And again, continuing with this theme on the brain, this is BIWAS, which is brain-wide association studies. And this is another sort of bombshell paper by Marek et al., again, brain new. They argue that data-driven combined brain behavior phenotypes will further advance our understanding of cognition and mental health, absolutely, for rare conditions. And we should remember that autism is a common rare disease or rare disorder. For rare clinical conditions, amassing large amounts of data is impossible, and we can do within-person induced effects approaches that's cost-effective. But if you need large neuroimaging data sets, then population sampling variability routinely results in inflated, irreproducible brain phenotype. So if you're trying the BIWAS, which is a particular statistical technique, that is not the only imaging technique available. But if you're attempting things like that, we need data sets with thousands of high quality processed samples. So the three vignettes that I just presented are all about data. And the AIF is also involved in some projects to generate data. And as we've discussed, long meaning longitudinal data, and wide meaning as many parameters as we can determine and afford to determine until we arrive at a feature selected set of data points that are most informative. So this is a quick plug for some of the things that we're doing. There is, along with the Stanford Medicine Tuam Foundations, and this is funded by Simons, this is a Count Precision Autism Pilot. This is an academic study that's trying to generate long-wide data for autism, molecular multiomics data and sensor data and other data. This is run by Mike Snyder at Stanford. And the pilot has just begun, which is with a very small cohort just to set a baseline and set infrastructure. But the eventual goal, the next one would be the target is eventually 10,000 individuals, if we can get there. And MOVE is measuring motion in autism. There is data that suggests that 87% of individuals with autism have motor defects, but motor assessment is not routine, and there is not a standardized motor assessment at the moment. And so here we're trying to generate data with Tuam Foundations, Rutgers, Strathclyde, and other places to make movement assessment routine. And going with Dae-Young's talk, the Tuam Foundation is collaborating, and the AIF is also involved in these collaborations with Amazon and to develop a data and analytics ecosystem that would provide a real-time feedback to individuals with autism and to their caregivers to leveraging data. So this would be sensor data, patch watch, like the mHealth type things, Amazon for data warehousing, camera data, maybe even activated by alerts from patch or watch, or sleep monitoring, which is non-contact based, and things like Nest to monitor CO2 temperatures in the room, exposometer, and Alexa. The idea eventually, the ambition is to deliver actionable information to parents and caregivers and to the autistic individual themselves for daily action. But to make all of this possible and reality, data sharing is vital. The one critical point, the only point if you have to take over from this talk, is that I think no single entity can ever have the volume of data required to address complex conditions like ASD. Siloed data are a drag on scientific and clinical advance. We just discussed that with respect to EHRs. And I would like to point out that de-identified EHR data, there's a whole slew of papers that show that de-identified data can be re-identified quite easily, actually. So de-identified data may not be the best way. It's useful, and there are newer techniques being developed for de-identification, but still it is not the ideal solution. And differing and often incompatible incentives for data sharing need to be rationalized. Technology now exists to allow this. By differing incentives, I mean that academics have the incentives of funding and credit and publications. Companies have the incentives for IP and of monetary incentives, and hospitals have an incentive to protect privacy and, again, to use their data internally or to monetize it in ways that are beneficial to them. So all of these incentives are incompatible, and for something that is a rare common disorder like ASD, it generally retards progress. And what do I mean by technologies that are available? Here, this is a quick cartoon, and I'm very happy to note I had some meetings with Andy and Dean. Very happy to know that Autism Speaks is already, like it has in so many other things, Autism Speaks is already pioneering application of these advanced technologies to autism, but there's more that needs to be done. And what is shown here is that 3 different hospitals, all of them have their data. And if you want to run a artificial intelligence algorithm on there, you need not centralize the data. They do not have to share their data. The data lives with the owner. It does not need to be exposed. A federated learning workflow is designed such that the algorithm travels to the data, runs locally, and returns a model. Nobody sees your data. Your data are not exposed. Privacy is completely protected. Your data is not centralized. You do not have to move the data. So this is what I mean when I say newer technologies exist to be able to leverage very large amounts of data that belong to very different entities that have very different and competing incentives. And federated learning is a complicated process, and Autism Canada, I should mention, and the Digital Tech Supercluster in Canada and Autism Speaks are involved in using it in an autism federated learning incentive. But it need not be that large scale. This is one of the companies that we are reviewing that we have not invested, so this is not a plug for them. They have flexible, secure data sharing models that do not need data transfer, that can run any algorithm, that can let you retain end-to-end control. Nobody sees your data, but the algorithm can run on it and return a model. So it's private, double-blind, flexible compute environment, on demand, in the owner's cloud, DevOps driven by API and UI. So the data sits where it sits. Here's a virtual vault that protects your data. Nothing is exposed. You can run any kind of computation you want on that. So fundamentally, the one message for my talk is that we need to really start using very large amounts of data, meaning it needs to be all of us for autism. We just spoke about all of us, so I don't need to belabor this. It's a volunteer cohort. ASD is not excluded, so there are probably some people with ASD there, at least one hopes, but not actively explored either. So that's a lost opportunity. As Dean pointed out at the beginning of this session, A pediatric cohort was not included, and that would have been very, very powerful to have it. But perhaps there needs to be a pediatric cohort or a long longitudinal follow-up cohort that is centered around autism, neurodevelopmental disorders, and associated complex conditions built on this model. So what we learned from this maybe should be leveraged on those things so that we can combine biology, environment, lifestyle, and behavior to actually have some concrete impact. Thank you very much for listening. And I need to thank various people from the AIF, my colleagues, and definitely credit to Mike Snyder and Elizabeth Horn for spearheading the COUNT project, which is the large-scale multiomics data project, and others who are founders of the AIF. Thank you very much.